Hey, it's the start of a new chapter, so you get me big again, briefly. This chapter is about something called eigenvalues and eigenvectors. We finished off chapter 4 by looking at Markov chains and saying what happens as you apply this same matrix over and over and over again. What's the long-term behavior? Eigenvalues and eigenvectors help us unpack the inner workings of a matrix over the long haul. It'll allow us to do some things more efficiently than we did with Markov chains. The two ideas are pretty closely tied together. So let's dive in, and I'll put myself down in the corner here. So think about what happens when you multiply a matrix times a vector. I've got a matrix here, I've got a vector here, I've got a constant here for some reason. We'll get to that in a minute. But let's think just in general what happens if you multiply some matrix times some vector. Maybe not these ones. So let's just say you've got some matrix B times some other vector U, and you get some vector as a result, like W. And if you think of those things graphically, you'd say maybe, U starts out down there, and after you apply this transformation to it, then maybe W, I don't know, looks like that or something, right? It turns it into some other vector, I guess is the point. And we looked at a whole bunch of those transformations back in chapter 2. But let's go ahead and unpack what happens with my particular example. Like, why does Abel have an example prepared already? Let's find out. So when you do A times V, 3, 2, 5, 6, and maybe let's just plot V. It's 2 over and 5 up, so 2 over 5 up. So V looks something like that. Okay, well, let's see what happens when you multiply A times V. I'll just do this by hand since it's 2 by 2. Let's see, that's going to be 6 plus 10 is 16, and on the bottom 10 plus 30 is 40. Okay, fine. You multiplied A times V, you got a new vector. But let's take a look at what V looks like. It's 16 over and 40 up. Sorry, it's not V, it's something else, but the result is now 16 over and 40 up. And that actually, if you're careful about it, goes exactly the same direction. It's actually off the edge of the screen here, but maybe we can break this down numerically. Let's factor an 8 out of this. That's the same thing. So the point here is that multiplying A times V does transform V, but it just makes it longer. It's in the same direction. So multiplying A times V is exactly the same effect as multiplying 8 times V. And instead of multiplying V by this matrix, we could have just multiplied V by this constant and saved ourselves some work. A doesn't do that to every vector, by the way. 2, 5 is special. A will take other vectors and swing them around and put them in different directions. But V in particular, when you multiply it by A, comes out the same thing as 8. So to shorthand this, we should say that A times V equals lambda times V. If you're not up on your Greek letters, by the way, this is lambda. Lambda? I can't remember if there's a B in there. I don't think so. I think it's just lambda, like that. Now I need to check. Hold on a second. Okay, so it does have a B. There you go. Who knew? Anyway, like a little lamb, lambda. It's just a Greek letter. It's an L. I don't know why they picked that particular one to be the eigenvalue or eigenvector, eigenvalue symbol. But they did. So anyway, this is the basic idea. Is anytime you've got a matrix and you find some vector, that multiplying the vector in the matrix is the same as multiplying a constant by the matrix, you have an eigenvector and you have the corresponding eigenvalue. So we could say for this matrix A, 3, 2, 5, 6, say something like 2, 5 is an eigenvector and that eigenvector has a corresponding eigenvalue of 8. And again, the usefulness here is just it's easier to multiply by 8 than it is to multiply by a vector, especially or by a matrix. Sorry, it's easier to multiply by 8 than it is by 3, 2, 5, 6. Especially if the vector is not a 2 by 2, but it's maybe a 10 by 10, and instead of multiplying by that, you can just multiply by 32 by a constant. That saves yourself a lot of work. Okay, so let's get our definition first of all. So here's the official book definition. It says the eigenvector of an n by n matrix, so we are looking at square matrices. So that's probably worth pointing out. This is going to be square. It is possible to have eigenvectors and values for non-square matrices, but we're not really going to look at those. And it's a non-zero vector, so obviously if you use the zero vector here, that sort of works trivially. But it's got to be a non-zero vector x such that multiplying the matrix times x is the same as multiplying a constant by x for some scalar, lambda. The scalar is called an eigenvalue if there's a non-trivial solution to this basic equation down here, and x is called the eigenvector and lambda is called the eigenvalue. Okay, so let's take a look at one more eigenvector for this particular matrix. It turns out that, here, let's call this V1. It turns out that negative 1, 1 is also an eigenvector for this matrix. So why don't you tell me what the corresponding eigenvalue is for that one. So take a minute, maybe pause the video, and let's just say that, oops, let's get on the right layer. Let's just rewrite this for our other eigenvector. So negative 1, 1 is an eigenvector with a corresponding eigenvalue of what? Okay, so pause the video for a second, just multiply the two together, see what you find. Okay, so hopefully when you multiply these two together, I'll do it real quick. When you do 3, 2, 5, 6 times negative 1, 1, that becomes negative 1, 1. You get the exact same thing coming out, which means that our corresponding eigenvalue is 1. All the steady state vectors that we looked at in Markov chains were eigenvectors with an eigenvalue of 1, right? Because you multiply that steady state vector by that transition matrix, you get the same result coming out. Okay, so this first video, we've basically just gotten the vocabulary and the idea. of an eigenvector and an eigenvalue. Of course, one of the big questions of this section is going to be finding them. If someone just gives you a matrix A, how can you find the 2, 5 and the negative 1, 1 and the 8 and the 1, right? The eigenvalues and the eigenvectors. So we'll look at that in the next video.